All right, welcome everyone. So the first speaker today is Vikash Mansinghka, who is a principal research scientist at MIT. Many of us commit some of our time and energy to studying probabilistic programming, but I don't think anyone commits as much time and energy as Vikash. I think is probably one of the leader of this community. I wanted to take a look at the list of languages that he has designed that are related to probabilistic programming. And so here's a non-exhaustive list. He contributed to Church, which most of us know because it was so influential. Picture, a probabilistic programming language for scene perception. Venture, a probabilistic programming language that explored the idea of programmable inference. BaseDB, probabilistic programming for database query. Gen, which is a general-purpose language that is currently working on. SPPL, a domain-specific probabilistic programming language for exact symbolic inference. And pclean, probabilistic programming for data cleaning. And as I said, there are others, but I don't want to spend too much time on this. He's also one of the founder of the Probabilistic Programming Conference. And finally, he's the author of the chapter on probabilistic programming in the new edition of the famous AI textbook, A Modern Approach, AI, A Modern Approach by Russell and Norvig. Today, he will talk about an alternate scaling route for intelligent systems via probabilistic programming. Welcome, Vikash.
Thank you, Jean-Baptiste, for the very kind introduction, and to you and the other organizers for this wonderful symposium. So, today, I'd like to cover three topics. First, I'd like to give one view on how probabilistic programming and intelligent systems relate. Then I'd like to give some examples that may help to illustrate that view by showing you probabilistic programs written in the Gen language that learn probabilistic program structure to predict structured data, including time series and databases, and that can infer 3D scenes from unstructured video. And then drawing on that, I'd like to reflect a little bit with you about prospects for scaling AI engineering using probabilistic programming. Now, before I get into the technical content, I just want to say that all the work here is really work that's done principally by wonderful students and some staff in the Probabilistic Computing Project. I especially want to highlight Marco Cusimano-Towner, who created the Gen probabilistic programming language. Firas Saad, who will be joining the faculty at CMU next year, and all the work on structure learning of probabilistic programs really comes out of his research. And Nishad Gathoskar, whose research on 3D scene perception you'll be seeing as one of the main examples. And also wonderful colleagues at MIT like Martin Renard and Josh Tenenbaum, who've helped mentor many of these students over the years. Okay, so let's dive into probabilistic programming. So the motivation for probabilistic programming from my viewpoint on AI comes from trying to understand how is it possible for intelligent systems to work computationally? How can they achieve human levels of robustness, data efficiency, flexibility, speed, and energy efficiency? And if we can build those AI systems, those kinds of AI systems, can we use them to explain and ultimately maybe quantitatively predict aspects of the mind, brain, and behavior? So those are the questions that motivate probabilistic programming. And there's two broad domains we've been studying these questions in that you'll see examples from in this talk. The first is common sense. And by common sense, I mean knowledge of the physical world, intentional agents operating in that world, the ability to perceive the structure of the physical world, that together allows this person here in the video to make some very interesting inferences when the adult performs this puzzling behavior of failing to put the books inside the cabinet. The kid somehow is able to infer what the adult was probably trying to do and generates a very useful response. So by common sense, I mean the knowledge that almost all humans acquire in the first couple years of life. By data-driven expertise, I mean knowledge like that depicted here in a project by the Gates Foundation to bring together data on millions of children with stakeholders from multiple disciplines. So here I mean the types of knowledge that adults acquire over the course of their professional expertise. We'll see examples of probabilistic programs that model aspects of both these facets of intelligence. And kind of the heart of what I'm calling the MIT view on probabilistic programming is in this picture. That one of the central problems of intelligence is that we have to make sense of the external world, perceiving our sense data using approximate models where we don't know the structure of the world, we don't know the current state of the world, let alone the future, and in many cases we're fundamentally uncertain about the basic laws by which the structure of the world evolves. The tools of computer science gives us fairly mature toolkits, actually, especially building on physics, to simulate the external world from a known world state and produce this, accurate sense data that an agent might perceive. But the tools from computer science for the mental simulations of the world, and in particular, simulations that account for fundamental uncertainty about the structure of models that approximate the world, that's much less mature. But that's where we think probabilistic programming may play a distinctive role. And the view of intelligence I just sketched is maybe interestingly a contrast with an increasingly popular view of intelligence as large-scale end-to-end neural modeling, where networks are trained to produce actions, in some cases directly from unstructured sense data. So, slightly more technically, the reason we think probabilistic programming gives us a distinctive approach on that core problem of intelligence is that it allows us to synthesize and integrate key ideas from multiple paradigms in AI, including symbolic programming, probabilistic inference in generative models, and learning from data, which most recently we maybe most strongly associate with neural networks or large differentiable programs. And it's really the ability to build systems that integrate all three of these perspectives that enables some of the progress in AI that we're most excited about. And one quick way to get a sense of that progress, maybe the most important slide in the talk is here. As Jean-Baptiste so kindly said, some of us have been working on probabilistic programming for a long time. But it's really only in the last maybe 2 years, a year and a half, that we've been able to have a slide like this, where we can take a diverse array of applications, specifically 3D scene perception, which we'll hear about later, common sense data cleaning from the pclean language by Alex Lev, which I won't present today, and automated data modeling that has learning models that forecast time series in databases. So 3 diverse domains, all with significant industry activity and a lot of research activity, where we've been able to build probabilistic programming systems that match or exceed state-of-the-art machine learning systems in accuracy, performance, and in some cases both. And that's a very recent development, at least from our perspective. And hopefully by the end of this talk, you'll understand some of the technical principles that are driving these results and what we think they might imply for the prospects for scaling AI engineering using probabilistic programming. Another distinctive feature of the view on probabilistic programming that you'll see in this talk is that it's not just about representing models as code. So we see there being at least 2 central ideas in probabilistic programming. The first is indeed to represent probabilistic models as programs that make random choices for all the latent variables. And you'll see examples of that in Gen later in this talk. But the second idea, which we think is maybe just as important, is that once we've made that first move, we can represent operations of inference as learning as metaprograms that produce or consume probabilistic programs. And that allows us to leverage powerful techniques from symbolic analysis and compilers to improve performance while preserving generality and automation for these operations. And in some cases, maybe get closer to the conceptual heart of what these operations mean mathematically. Now, the field has been exploring these ideas in a range of languages. And I think maybe most of the emphasis, especially from a user perspective, has been on languages that try to automate inference. Maybe most well-known, the Stan language as an example of this. And these languages that support automatic inference have naturally concentrated on more restricted domains of problems. There are some languages that afford varying degrees of programmability for inference, and I'll show some examples of that in Gen later in this talk. But my hope is that you'll see that really by embracing this second idea in probabilistic programming, we can get new answers to some of the fundamental computational trade-offs in probabilistic programming and intelligent system design. So we saw a slide like this in Marina Gronova's wonderful talk yesterday. There are fundamental computational trade-offs that you see in theoretical computer science and in programming languages between the desiderata of generality, automation, and metrics such as accuracy, efficiency, and reliability. It's sort of hard to have all three at once. And one view on AI is that sort of the hard problem of intelligence is how to somehow have all three of these at the same time while giving up on just a little bit up here to allow for various forms of human error. So somehow intelligent systems can give the illusion of solving very general problems automatically, and actually in practice with really striking reliability, efficiency, and even accuracy. So how is that possible? And one reading of probabilistic programming is that it gives us new tools for exploring these trade-offs for a much broader class of models than those supported by platforms like TensorFlow and PyTorch. And so to explore those trade-offs, we've been building a stack that includes programs representing models or generative programs and programs representing inference algorithms or inference programs to build application DSLs for common sense and data-driven expertise, and then a stack of abstractions for efficiently implementing those probabilistic programs, and also exploring the hardware abstractions that are needed to achieve greater levels of energy efficiency by exploiting parallelism and latency. And most recently, some progress on connecting probabilistic programs to models of biological neurons. And we think this whole stack is going to be needed to exploit the full potential of probabilistic programming. Okay, so let's look at some example probabilistic programs in Gen. So just a few words on Gen. So Gen has been developed over a number of years by several students, created principally by Marco Cusimano-Towner. It's an open source research prototype at the present, but it has been used in battle conditions by both industry and academic collaborators of ours, as well as academic and industry users who we don't know. So we'll occasionally see papers written that describe applications of Gen. The open source community is, I would say, small but existent and growing. So we've had contributed tutorials in systems biology and some in computational cognitive science. You'll see that a distinctive feature of Gen is its programmability and extensibility. And here I'm sort of referring to some of the really interesting requests from Nicolas Chopin's talk yesterday. So one key feature of Gen's design is that the user has to supply not just a model represented as a generative program, but also an inference program. This is in contrast to the model where the user to the programming model where the user just specifies a probabilistic model. Now, the challenge with the picture on the left here, where the inference is automated, is that it's hard to get good performance outside of restricted problem classes. But the degree of freedom of this inference program allows the user to customize the algorithm for the problem at hand, as well as implement general, generic, so-called universal inference algorithms that may be too inaccurate or slow in many cases, but in user space as opposed to inside the language implementation. A second key feature of Gen is that it has compilers and support for extensible compilers for embedded DSLs, so that the languages for generative programs can strike a wide range of expressiveness and performance trade-offs. And it's that facility that allows the compiler to produce fast, automatically specialized implementations. So that code for doing inference in parametric regression models or Bayes nets doesn't have the overhead of code in general languages that might have stochastic control flow. Gen supports a broad range of inference primitives in its user space libraries. So these are all implemented in user space using a set of inference primitives, which I won't go, lower level primitives, which I won't go into in this talk. But they span the Monte Carlo variational optimization and neural approaches, as well as some symbolic or exact algorithms. Maybe I'll come back to this slide later. I think it's maybe the most important to say that Gen's performance turns out to be competitive with more restricted probabilistic programming languages. So these are just a couple benchmarks from our PLDI paper back in 2019, comparing Gen on a couple of useful micro benchmarks to systems like Venture from our lab, which is quite slow by comparison, and systems like Stan and Edward and Anglican and Turing. I'd say, from my perspective, the most important feature of Gen is it's the first probabilistic programming language that I've personally felt was expressive and performant enough to teach to a large number of students. And so with Gen, we've started to see new students come in and in their first year write papers at the end of their first year for NeurIPS that solve problems that we were scared to assign as master's projects just a few years before. So it's not easy to use by any means, but it does seem to be usable in practice. Okay, so let's look at some examples in more detail. So here's a problem where data is coming in one data point at a time, and I'd like you to sketch in the air with your finger the curve that you think is behind the data. Okay, so some people are saying maybe there's a periodic overlay and a linear trend, a linear rise. Okay. So let's write probabilistic programs that can learn the structure of these probabilistic programs from data. So here, what you're seeing on the right is the structure and parameters of a probabilistic program in Gen that's being learned from the data stream on the left. And you're seeing the forecasts overlaid in green. And you can see the predictions go through many of the qualitative patterns that you probably saw in your mind's eye when you were looking at the data. And so crucially, as new data comes in, it's not just the parameters of this program that are changing, but also the program structure. And if we aggregate across an ensemble of 64 programs, we can look at forecasts that maybe better match the pictures in our mind's eye. That make graded phase transitions between regimes where there's broad uncertainty to regimes where there's a periodic overlay and a linear trend. Now, one measure of progress on this problem is that in Gen, we've been able to get the performance of this application to compete with serious AutoML systems, both Bayesian and neural, for time series forecasting that were developed in industry. So for example, here I'm showing a comparison to Facebook's Profit system, both in its normal form and with a custom extension to incorporate the right model structure. And the performance of the probabilistic program structure learning system is comparable in runtime, but I think the predictions are qualitatively more reasonable. And our papers have quantitative evaluations of accuracy that you can look at if you're interested. The comparisons are actually a bit more favorable when you compare this approach to strong neural time series forecasting systems, such as the neural profit system that was more recently developed. But one of my favorite features of this approach is a distinctive feature of human cognition about data, which is the ability to deal with shocking events in the world that might cause a big change in one's predictions. So here, it turns out the data you were seeing were measures of airline passenger volume, which, as we know, crashed abruptly at the start of the COVID pandemic. And it turns out if we show this data to our probabilistic program structure learning algorithm, it detects the change point and adapts its forecasts rapidly. And that's in contrast, again, to the strong baselines like Facebook Profit, even when we modify Facebook Prophet to have a custom change point in its hypothesis class. So the parameter estimation procedure in Facebook Prophet doesn't scale when you extend the model to the greater expressiveness that's needed to capture this phenomenon. And Neural Prophet also fails on this problem. So let's reflect on sort of how probabilistic programming helped us get here. So here on the top, I'm showing the number of lines of code it takes to implement this system in Gen. We'll look at the code in just a minute. Versus the automated statistician, a non-Bayesian variant of this basic setup that was built principally by James Lloyd and Dave Duveneau from Zubin Garamani's group. And I know Jan Willem actually also worked on an early probabilistic programming implementation of this kind of thing in Anglican. Now, the Gen implementation is significantly shorter, but I think it's a measure of progress I'm really excited about is that it's actually also competitive in performance with efficient Julia implementations of the same procedure. So several years ago, we had a paper implementing this approach in Venture, and its distinctive feature was we were Bayesian about the structure, the unknown model structure, but we were a lot slower than we knew that the system ought to be. But now we can be Bayesian about model structure online and compete in raw performance with carefully optimized handwritten implementations. So how did we do this? Well, first, we have to write a probabilistic program that somehow generates these random Gaussian process programs in a little DSL, where I'm showing the source code here and the types of time series they generate on the bottom. And we do that by writing a recursion that stochastically generates the abstract syntax tree for the DSL program using a probabilistic context-free grammar prior. And this approach, which is very closely related to something Andrew was talking about yesterday, essentially introduces a broad ignorance prior over DSL programs. So we're using probabilistic modeling not to encode narrow prior knowledge, but broad ignorance. And that's actually a fundamental principle for many of the AI engineering applications that you'll see in my talk and from my lab. The purpose of probability is to properly account for our ignorance, as opposed to more kind of precisely constrain our hypotheses based on knowledge. Now, how did we do inference? Well, we wrote an inference program using the inference metaprogramming facilities that Gen provides. And the basic algorithm template, I won't go into the details here, but the algorithm template is resample move sequential Monte Carlo, which takes a collection of, which goes back to Jilks and Berrezzini in 2001, but we've had a series of papers that implement successively more general versions of it in probabilistic programming languages. I recommend you check those papers out if you're interested in sort of sophisticated SMC techniques that combine SMC with MCMC. So in resample move SMC, one initializes particles, reweights them and resamples them, but then perturbs them with an MCMC kernel that leaves some target distribution invariant and then reweights. And on the left, I'm showing a user space implementation of resample move SMC in Gen, which invokes some procedures for Hamiltonian Monte Carlo rejuvenation and reversible jump over these abstract syntax trees that I'll give you a little more detail about in a minute. But a key point is that resample move SMC is significantly more compute efficient than MCMC for this problem of structure learning. So the red curve shows error decreasing rapidly for resample move SMC versus the black curve for a typical run of MCMC for this problem. So what about that MCMC update step? So we have to make changes to an abstract syntax tree representing a probabilistic program. And we do that using a technique called involutive MCMC, which was actually developed independently by a couple of groups. Marco Cusimano-Towner came up with a version of it in Gen. Max Welling's group came up with a version of it. Some of the versions out of Max Welling's group actually explored really beautiful modern sort of variants of classic MCMC algorithms that you can express in this framework. Marco really focused on how do you automate calculations of the accept-reject step by combining ideas from probabilistic programming with automatic differentiation to calculate the Jacobian correction that you need for involutive MCMC. But it turns out that this type of rejuvenation is really essential. So on the left, I'm showing forecasting for this resample move SMC program with the custom rejuvenation over model structure. And on the right, I'm showing what happens if you use a generic SMC inference algorithm. And this performance is pretty typical, that the generic SMC method, the particles often collapse, the structured learning can underfit, whereas the more sophisticated algorithm actually can track changes in the posterior over structure that arise only when there's sufficient data to resolve that structure. And Ferraz's dissertation has really shown how to implement this basic picture of going from data to learn the structure of probabilistic programs in languages where you can do exact symbolic inference for a range of types of data: time series data, panel data, cross-sectional data, and relational data. And for a range of questions, I'll just show a little bit more about that here. But the high-level point of this slide is that I expect probabilistic programs will increasingly be written at least partly by machine and learned from data in the context of DSLs and ignorance priors that are specified by statistically sophisticated probabilistic programming language engineers. And so, one system that's explored the same basic idea in the context of databases is called Inference QL. It's a more recent version of a system called BaseDB, built in part by Ulrich Schechtel. And I won't go into the details of Inference QL, but just to give you a feeling for it, it does online structure learning for database tables. And you can use it to generate synthetic data. Here, so the orange dots on all these plots are synthetic data, and the black dots are real data. And this plot here is showing Inference QL. And these two plots are showing synthetic data from a strong baseline, actually, from a colleague at MIT who has a startup that has an open source backend that we're comparing to. And so the probabilistic program structure learning is actually significantly faster and more accurate than, for example, neural network methods, as well as some more classic copula methods from statistics, which we might expect to underfit for generic databases. And Inference QL allows the learned models to be queried in a SQL-like language. So for example, you could take a data table and ask questions like, find the rows, in this case satellites, that have unlikely values for some column, like let's say the orbital period, and expose that in a SQL-like notation. So our thought is that this plus structure learning gives one path to make probabilistic programming usable by a much broader audience of developers. Okay. So let me talk a little bit about inferring 3D scenes from unstructured data, a very different context. So here I'm showing input RGB and depth images. And on the right, I'm showing the outputs of 3DP3 on this data, which include a depth reconstruction that suppresses noise in the depth image, which comes from a scene graph showing the flush contacts between the objects in the scene. And those objects are modeled by voxels, so low-resolution graphics models that can generically model a broad range of artificial and natural objects. And this is work by Nishad Gothaskar from NeurIPS 2021. And one of the surprises for us was that it was possible with our current toolkit to compete with state-of-the-art deep learning systems for 6 degree of freedom pose estimation from real-world video. So on the top, I'm showing some scenes and the output poses of key objects from Dense Fusion, which is a deep learning system from Stanford. And on the bottom, I'm showing outputs from 3DP3 for those same objects in those same scenes. I'll give a quantitative view of the results later, but the key point is that we're sometimes able to detect and correct very large errors that are made by deep learning systems. And although we are significantly slower, we're actually still suitable for real-time applications. And you'll see some more on the performance engineering in just a moment. I won't go into the details of the quantitative evaluation, but I will say that we've evaluated 3DP3 on thousands of household scenes from the well-known YCB video benchmark in robotics. And it turns out we're quite a bit more accurate and also more robust than the Dense Fusion deep learning baseline, although there's a lot of room for improvement. And I'm happy to talk about where the system falls flat as well for people who are interested. So for this community, I think it's worth just reflecting on how we got there from a probabilistic programming perspective. So here is the main generative function for 3DP3, which has a prior over object shapes and scene graph structures that are then parameterized to produce something from which 6 degree of freedom poses can be calculated, and then images rendered. And then noise to model noisy, added to model noisy point clouds that are observed from real sensors. So it's a generative program, but it's not really about photorealistic graphics. It's really generating very rough, low-resolution geometry. So let's just dig into that a little bit. What's the likelihood that closes the simulation to reality gap in this setting, which, as we can see, is maybe significant? So the basic trick we tried in 3DP3 was to use a mixture model that allows any depth point to be generated by any latent voxel, just essentially via mixture, that concentrates its mass within a bounded radius, R. So as the radius grows, the geometric resolution drops. And this is what allows us to model, really rough real-world point cloud data without getting lost in the details of the noise. Now we can learn object models in 3DP3 from data, essentially by solving a SLAM problem. So here I'm showing 5 real images and the learned model of the object's shape, where the system knows that it knows the outer shape of the mug, but it doesn't know what's inside the mug because it hasn't seen any data. And the poses of the camera viewpoints as well as the object shape are all inferred from data to learn the models. So we think a version of this might be extendable to handle the open world of objects if we can somehow put a non-parametric prior on object shape and do online structure learning like you saw earlier. So stay tuned. We're trying to get that to work right now. So how do we do inference? Just in broad strokes, we still do a kind of resample move SMC, but we use data-driven neural proposals that are learned on synthetic data and involutive MCMC fine-tuning of the scene graph structure. And the math for this kind of complicated, messy-looking algorithm, it's automated by Gen. And I'm not sure we would have succeeded in building the sampler if we didn't have the advantage of probabilistic programming infrastructure with programmable inference and high performance. So when I say I think we're at an interesting inflection point, it's really because I feel like we're now able to tackle problems that have engineering complexity that we would have been daunted by a few years ago. And I won't go into the details of how we search the space of scene graphs, but I do want to highlight a mathematical principle that's crucial for performance engineering for probabilistic programs that may be of interest to the SMC researchers in this audience. So how do we speed up the scoring of these likelihoods? Because otherwise we've got a likelihood term that scales as the number of point cloud data points that we're trying to model, which is not good. Gen is designed to allow for extensible embedded DSLs. Alex Lev, a wonderful student in the group, has been working on a DSL called Prox, which allows you to stick density approximations of a class that's unbiased using sound by construction probabilistic programming to guarantee that the estimators are valid. And this can actually produce substantial speedups, essentially yielding pseudo-marginal versions of all the inference algorithms in Gen. So for people who are familiar with pseudo-marginal methods, Gen supports them natively but doesn't make it easy to safely implement them, and Prox adds the automation that's needed for safe pseudo-marginal SMC and MCMC, and actually versions of variational inference that use pseudo-marginal estimation. I won't show the code or go into the code for the Prox example, but I will say the mathematical principle here is worth reflecting on. So if we have a probabilistic program which induces a joint density, z and x, over traces, that might be intractable because actually the traces have some auxiliary variables u, like let's say the mixture indicators in the previous example, then the trace density is intractable because that requires integrating out u. The key principle of pseudo-marginal estimation is that you can form an importance sampling estimator for that intractable marginal density by having a proposal that infers u given z and x. Since this is probabilistic programming, we can automate the construction of those queues using probabilistic programming. And if we have the right machinery, we can then use these unbiased estimates which happen to have 0 variance when our Q is the exact posterior over U, as a way of essentially integrating out approximately, lots of nuisance variables in our trace. And in fact, you can apply this principle recursively to arbitrary depth. We've done some work trying to show how this principle of compositional inference can be used to unify a broad range of families of approximate inference. And this is work that came out in UAI this year, principally by Alex Lev, called RAVI, or recursive auxiliary variable inference. And so for people who are interested in probabilistic programming with sophisticated pseudo-marginal methods, or hybrids of Monte Carlo, variational inference, and dynamic programming, I encourage you to check it out, because it expands the design space. And it turns out that supporting Ravi required no extensions to the Monte Carlo interfaces in Gen, and a few small patches to the interfaces for gradients to better support stable estimators of elbows and U-bows. And the papers go into some detail about that. Okay, so let me just say a couple words about scaling up AI engineering, and here's some questions. So I started the talk by sort of contrasting this picture of large-scale neural modeling, where sense data gets fed into a fast computation to produce actions, with a view of AI systems that infer the structure of the world and account for their uncertainty. But of course, this neural approach has seen enormous success, especially recently, and it scales in some very surprising ways. It's sort of an empirical success story. And there is an increasingly popular hypothesis that if we just keep sort of pouring resources into it, this will eventually match and exceed human general intelligence. And I think, 5 years ago, this wasn't taken too seriously, and I think it is being taken increasingly seriously now, although I think it has there's lots of reasons to be very skeptical of this. There are well-known phenomena of brittleness with large-scale neural nets. So here I'm showing at the Tesla full self-driving system, misperceiving traffic lights flying down it on the roadway and braking because it's driving behind a truck carrying traffic lights. And this type of brittleness is not unusual. There's also an exponential growth in network size that seem necessary to keep driving improvements in performance, even for fairly simple problems like 2-digit addition, which we know how to solve much more efficiently by symbolic methods. So there's an alternative hypothesis which says neural nets are one tool in a toolkit that can integrate symbolic, probabilistic, and differentiable computation that will asymptote well below human intelligence on its own. But that if we have tools that can account for inferring the structure of models of the world and accounting for uncertainty, which we seem to have at least some progress towards such tools, as measured at least implicitly by a range of applications, then maybe there's a scaling route that could get us farther. We don't know how far it'll go, and there's fundamental computer science reasons to ask about whether what it would look like for this curve to eventually kind of cross human level intelligence. We're certainly a very long way away from that. We're even before the exciting point on this curve. But I'm trying to give you a feeling for why we think things might start getting a little bit more rapid and interesting for probabilistic programming. The basic reason is that we're taking principles that enabled the scaling of neural nets, but expanding it to just a broader range of models and a much broader range of inference techniques. And that, in turn, lets us do much more modular online forms of structure learning, which may have a very different scaling behavior than end-to-end learning of neural nets. And so I think just in the interest of time, I'll close with this slide. So we could ask ourselves, what might it look like to try to find scaling laws for probabilistic programming that allow the field to organize research in the way that scaling laws for large neural language models organized research in that subfield. And we don't know the answers yet, but we're actively working on pilot experiments along all three of these, just as initial hypotheses. So one question we're asking is, how costly is accurate inference for the problems of online structural learning? So if we want better posterior KL divergence, how much training cost is required for priors that lead to varying code and trace size? And how valuable is accurate inference? So how does predictive KL divergence vary as a function of posterior KL divergence? And then if we can use PPL structural learning to learn models of the world, how much cheaper is it to use those models versus trying to reason from language alone? So in particular, if we ask an AI system to answer questions about data, what's the probability the AI system gets it right versus training cost for just using a neural model on its own versus learning a probabilistic program and learning to map English to a query against that probabilistic program? So hopefully that gives you a feeling for how some of the ways we think inference and probabilistic programs might help us scale to larger AI systems. Okay, thank you very much.